Okay, in this unit, Electrochemistry, we begin by studying the nature of redox reactions. These, otherwise known as electron transfer reactions. So you can see I have two photographs here, one of the before on the left and after on the right. And I'm showing a piece of copper wire. You can see the shiny orange ductile solid placed in a colorless solution of silver nitrate. Now it's true that this has already started to darken on the surface of the copper wire, and that's because in the time it took me to combine these and then take the photo, there already was some evidence of chemical change. Initially, the copper wire below the surface was just as orange and shiny as you see it is above. After a period of time, and this photo was taken about 24 hours later, you see the blue solution and this solid formed, and I've labeled the products for you here. So we see copper wire in the presence of silver nitrate solution forms the silver solid and the copper 2 nitrate. Now you may recognize that as a single displacement reaction pattern from your earlier studies. But let's look at what's happening to the specific entities in solution. When we have copper wire, this copper wire is made of neutral atoms of copper. So the entire copper wire, these are all neutral atoms. And that's what I am showing in this equation here. These are neutral atoms that make up a metal. Now, where's the copper present on the diagram on the right? Well, the reason the solution is blue is because of the copper 2 ions that are in solution. And so we've formed copper 2 ions. Now, this equation is balanced for mass. There's one copper, as you know, one copper here and one copper ion. Again, the change of electrons is not significantly changing the mass. So we're balanced for mass. Now, what about charge? How does a copper atom become a cation? Does it gain or lose electrons? Hopefully you've decided it loses electrons. And in this case, 2 electrons are lost in order to become a copper 2 positive ion. So we call this half reaction. It's half of the chemistry that's happening in the test tube. So we call this an oxidation half reaction. The idea of oxidation here, we can see that the copper atom is losing electrons. And so to lose electrons is oxidation. You might think of the name Leo, lose electrons oxidation, to help remember that. Now what's happening on the silver side of things? Well, originally we had silver nitrate in solution, and so we had silver ions. And now we have formed, as you can see right here, neutral atoms. Again, a metal as a solid are neutral atoms. And so those silver ions have become silver atoms. So, have these silver ions gained or lost electrons? Hopefully you're thinking that each silver ion has to gain 1 electron in order to form the silver solid. So a gain of electrons, when a substance gains electrons, we call that a reduction. And so we have G for gain, E for electrons, R for reduction. So Leo the lion growls, Leo goes grr. So lose electrons is oxidation, gain electrons is reduction. So we've written 2 half reactions here. Now, let's make sure that the total electrons lost and gained are equal so that we can come up with a balanced equation for the overall reaction. So as we look here and see that there are 2 electrons lost and only 1 electron gained on this side, I'll need to multiply the second equation by 2 here in order to have 1 copper atom losing 2 electrons and 2 silver ions picking up those 2 electrons to form the 2 silver. And so the 2 electrons lost and gained will be canceled, and that will leave us with the copper solid plus 2 of the silver ions reacting to form the copper 2 ions in solution and 2 silver solid. And so this is actually then the net ionic equation for the reduction and oxidation that's occurring. And we call this overall reaction a redox reaction. The idea that there's reduction of one substance and oxidation of another together is called a redox reaction. Okay, so you can see that the copper solid is being oxidized and the silver ion is being reduced. And together, those are two half reactions that make up the overall reaction, which we call a redox reaction. The simultaneous occurrence of both those reduction and oxidation half reactions. You'll notice I indicated that these two reactions here are the half reactions. Now, the only reason we multiplied by 2 for the silver ion reduction half reaction was to write the overall equation. And so to just write the half reaction for the silver ion, it's enough to say what I wrote in blue, that the silver ion plus the 1 electron produces the silver solid. Okay, so you'll see that I've labeled the copper solid as the Ra, or reducing agent, and the silver ion as the oxidizing agent. So how do we decide which is which? Well, remember that the oxidation and reduction half reactions occur simultaneously. One doesn't happen without the other. The copper wire was only oxidized because of the silver ions in solution, and vice versa with the silver ions. And so when we know that the copper solid is the substance being oxidized and the silver ion is the substance being reduced, the silver ion is being reduced because of the presence of the copper solid. So it is the agent or the cause of the reduction of the silver ion. And so copper solid is the reducing agent, causing the silver ion to be reduced. Similarly, the silver ion, because of the presence of it, is the copper is being oxidized, and so the silver ion is called the oxidizing agent. You'll notice that it always works that the substance being reduced is the oxidizing agent. Because of the presence of that substance, the other reagent is being oxidized. Okay, so for a bit of practice here, try this example. So write the oxidation and reduction half reactions and label the oxidizing and reducing agents. Okay, so you'll see that I pulled the 2 zinc particles out of the overall equation to begin this half reaction. And notice that the neutral atoms of zinc will lose 2 electrons to form the zinc cations, positive 2 charge. The chromium ions, on the other hand, will gain 3 electrons to form the chromium metal, these neutral atoms. So Leo, lose electrons oxidation, here we go, and Gur, gain electrons reduction. So the chromium half reaction is the reduction half reaction. Now, I didn't ask you to balance the overall equation, but the one that I gave you was not balanced for charge, so we'll just suggest what's coming up in a future lesson here by multiplying this equation by 3 in order to make this total electrons lost equal the total gained. I'll have to double the one below, and so we finish up with the 3 zinc solid and the 2 chromium 3 positive ions, forming the 3 zinc ions and the 2 chromium. Notice that the total electrons lost and gained are equal, and so those 6 electrons cancel. And so yes, there should be coefficients up here to write that equation properly. Okay, labeling the oxidizing and reducing agents. So for the 2 reactants, zinc and chromium 3 positive ions, which substance is causing the oxidation of the other? Well, if zinc is being oxidized, then that makes it the reducing agent. The chromium ions that are being reduced are then the oxidizing agent. Okay, the next part of the lesson is about oxidation numbers, and this is a super important concept. The oxidation numbers are essentially a bookkeeping system of integer values that we use to help us identify redox reactions, identify which substances are being oxidized and reduced, and we'll use them to help us balance redox reactions. So I'm going to be doing examples of each step in this table from your textbook. I'll be doing more examples just to help solidify the concept. So you'll find this table on page 603 of your textbook. So you can see in row A here that using the heading of the column, the oxidation number of an atom in an element is 0. So you'll notice in the examples that they've provided here, sodium solid is an element. Oxidation number would be 0. Oxygen gas is an element. One type of atom present, just oxygen. Oxidation number 0. Ozone is another form of elemental oxygen, although not the one that we're most familiar with. And the oxidation number of oxygen here is 0. And mercury, for example. So a couple more examples down here. Magnesium. Magnesium is just an element here, one type of atom, and so I assigned the oxidation number to be 0. Bromine liquid. Again, one type of atom, oxidation number is 0. So I'm using a different colored utensil in order to indicate the oxidation numbers. So we're going to be writing positive and negative integer values, or possibly 0, above atoms in compounds or elements. And so that's our first rule. Now to continue on, for row B, the oxidation number of a monatomic ion is the same as its charge. So you may see the formula CuCl2. And so it's up to you to recognize that as an ionic compound made of the copper 2 ion and the chloride ion. And so the charge on that single atom ion of copper is 2 positive, and so the oxidation number is positive 2. The charge on the chloride ion is -1, and so the oxidation number on the chloride ion is -1. Now will you sometimes, as we saw in the earlier example, just see the ion written on its own? Absolutely. And so the chromium ion here with a charge of 3 positive has an oxidation number of positive 3. Okay, for row C, I don't think there's too much else to show you here. You'll notice that fluorine shows up in both these compounds, and the oxidation number of the fluorine would be -1 in each case. For rule D there, as soon as you see oxygen in a compound, the oxidation number is -2. As soon as you see it. There will be only one exception. Whoops, -2, -2. There will be only one exception, and that is in the case of peroxides. So the example they've shown up here is hydrogen peroxide. Remember the idea of the hydrogen ion and the peroxide ion? We cross charges down. So we'll get a 1 here and a 2 here. And with the 1 outside the brackets, we don't write the brackets, so we end up with H2O2. In this case, the oxidation number for the oxygen is -1. So that is an exception and happens rarely. So most of the time then, when you see oxygen in a compound, the oxidation number is -2. Okay, last rule, row E here, is that the oxidation number of hydrogen is +1 in compounds. And you'll notice here I've written a bunch of examples. So hydrogen showing up in methane here, oxidation number +1. Hydrogen showing up here in methanol, and again here, +1. The hydrogen in water, +1. The hydrogen in hydrogen peroxide, +1. The hydrogen in hydrogen chloride or in solution hydrochloric acid would be +1. There is an exception, and the only time hydrogen does not have that +1 oxidation number when it's in a compound is in the case of a metal hydride. So for example, magnesium hydride, which happens, that ion forms when the hydrogen atom gains 1 electron to become stable. We cross our charges down and we'll have MgH2. In this case, the oxidation number of the hydrogen is -1. So this kind of reverts back to our rule about monatomic ions. If you recognize that the hydride ion has a -1 charge, you'll recognize that -1 oxidation number. Similarly, for the magnesium, we would have assigned +2. Okay, so those are all the rules to know. Now, it's true in each rule. For example, row D, I only assigned the oxidation number to hydrogen. Well, what about the oxidation number of the sulfur in this case? So let's look at how that works. So we have SO3, and we assign the oxidation number of -2 to the oxygen. Now what we need to figure out is the oxidation number of the sulfur, and we don't have that for many of our rules. So the idea is to call it X, fill in any subscript of 1 that you don't see, and set up an equation, an algebraic equation, to solve for X. So the subscript, the 1, times the X, plus the 3 subscript times the oxidation number here, needs to equal 0. And why 0? Because what I wrote in blue, the formula here, was overall neutral. I'll show you a polyatomic ion in a moment, but for now, let's go ahead and solve for X. And so we work out X minus 6 equals 0, so we swing the -6 over, become +6, and we finish with +6. And so the oxidation number on the sulfur here is +6. Now, what if we had sodium sulfite? So Na2SO3. Well, hopefully you'll recognize here that we have the sodium ion, Na+1. That tells us the sodium is +1, and that we have the sulfite ion here, SO3 -2. So my original example here was sulfur trioxide, a neutral molecular compound, and here we have an ionic compound, sodium sulfite. So the oxidation number of the sodium is +1. It's a single atom ion, just like rule B back up here. Now for the sulfite, we know the oxygen to be -2 because oxygen is always -2 in a compound except for peroxide, so I'll call the sulfur X. And so I follow the rule of subscript times the oxidation number, so 2 times +1 plus 1 times X plus 3 times -2, and that will equal 0, again because this, what I wrote in blue, the overall formula of Na2SO3 is neutral. And so 2 times 1 is 2 plus X minus 6 equals 0. 2 minus 6 is -4, and X equals +4. And so we see that the charge on the sulfur, or the oxidation number on the sulfur, is +4. Now, could you have solved that just working with the polyatomic ion of the sulfite ion? Certainly you could have. We would assign the oxidation number to be -2, call the sulfur X, fill in the subscript, and set up our equation. 1 plus X plus 3 times -2. Now in this case, notice that the particle is not overall neutral. Notice what I wrote in blue here. There's a charge of -2. That's why I have the -2 here. What I wrote in blue here was overall neutral. That's why this equation equals 0. Same thing here. The equation equals 0. And so we go ahead and solve. So we'll have X minus 6 equals -2. X is going to be -2 plus 6, and we'll see X equals +4. Okay, so this skill of being able to assign oxidation numbers is a critical skill in the unit. And really, everything we do in the unit after today comes back to this lesson, being able to identify oxidation and reduction processes that are occurring, and to write those half reactions, assign oxidation numbers, and recognize oxidizing and reducing agents. Okay, just to summarize then and consolidate all of the ideas, now we can use oxidation numbers and assign those across the top of all of the symbols of elements in each reactant and product. So for copper solid, we see that's a neutral atom neutral element here. Copper, we assign oxidation number of 0. The silver ion is a single atom ion, positive 1. The copper ion, a single atom ion, monatomic, positive 2. And silver solid, we see the element. So notice here that the oxidation number for the copper is changing from 0 to positive 2. The copper is being oxidized. The idea here is that it's losing 2 electrons. The copper is being oxidized. The silver ion, you'll see the oxidation number is changing from positive 1 to 0. And this is a gain of 1 electron per silver ion. And so gain electrons is reduction. And so the silver ion is being reduced. So when we assign oxidation numbers, it's very helpful to notice, and maybe you want to think of a vertical number line. So I'll put the 0 here, positive 1, positive 2, right? Negative numbers would come down below. You'll notice that the copper oxidation number is going from 0 to positive 2. It's being oxidized. And the oxidation number of the silver ion is going from positive 1 to 0. It's being reduced. And so that is a very helpful schematic right here. That's very helpful to use. So I would keep that in mind. As you assign oxidation numbers, you'll see that the substance that is being oxidized is always the substance whose oxidation number is increasing. So the zinc is moving from 0 to positive 2. So on a number line going from 0 up to positive 2, that's oxidation. And so the zinc is being oxidized. That makes it the reducing agent. The chromium, on the other hand, is going from positive 3 down to 0. The oxidation number is decreasing. This substance is being reduced. And so that would make it the oxidizing agent. And so assigning oxidation numbers is a very quick method of seeing which substance is being oxidized and reduced and identifying the oxidizing and reducing agents. If you were to assign oxidation numbers across all the elements and no element has their oxidation number changing, then that reaction is in fact not even a redox reaction.